Hello. Good morning to my fellow attendants in this morning. Every Thursday we have a webinars for new SolidWorks topics to help you to improve the productivities during your modeling, design, and analysis. And this week, the topic would be game time with SolidWorks simulations. And I am Sean Yap, the application engineer in CADVision. Now, I personally think this is a very interesting topic. Basically, what we're talking about today is about simulation motion. Okay? To simulate the kinematics and dynamics design mechanisms in SolidWorks. Okay? So let's learn this by doing something fun. Okay? I have brought to you two case studies to let you go through the process in setting up a motion simulation, as well as try to optimize the design to improve the design via optimization. Right? I think it's good to learn this by fun, so I bring you two models. Right? One is the Catapult. Right? The other one is the basketball throwing problems. Right. Let us just begin with where we can find motion interface. Right. Actually, it's just right next to your model. If you look at the downside, at the right of your models, you will find a tab. It's called Motion Study 1 tab. Right. If you click on it, right, you will find that some tab is coming up, right, and you see a lot of stuff, right. But do note that the first you open it, the default would be animators. You can set it from here. Right, actually it's writing animators. Okay. So before you step into a motion simulation, probably you have already used animators. Right? So what is the difference? I would like to begin with what is the difference between animators and motion simulations. Okay. Let's look at the hierarchy of motions. First we have animator, and then we have basic motion and motion analysis. The animation wizard inside animators actually refers to some positioning effects such as rotation, your exploded wheel, or collapse animations. Right? So basically the character of it is to use key point to control. Right? You can see a lot of crystal over here. Those we call key point. Right? When we make some changes, let's say I want to put some of the part in 2 seconds, move to some place, I just go to that time and move my part, like what I'm doing my assemblies. I just move it, right? So the workflow is like this, right? Position the key point in your time bar, move the component, right? Set some properties, could be appearance, colors, transparency, so on and so forth. Right? And then they will leave a trace. For example, here is one key point, and then we will have another key point here. Okay? So you're basically going to adjust a lot of stuff. Right? So it is suitable for simple mechanism where there is no involve of physics. Right? There is, which means that we are not looking into the mass, momentum, contact, friction, and gravity when we're doing these animators. Okay. So what about basic motions and motion analysis? Yes, it involves physics. Right? It is used to analyze kinematic mechanism, right? Or sometimes we use it to generate realistic animations. Right? Here is a table for you to check on the comparison between three of them. Right? As we can see, animations, right? We support key points, mates, and moto. Okay, basically it's controlled by key point. Right? If you have built up the mate, right, of course you can use a motor to drive more than one component. Right? However, in basic motions, we are not using key point to control anymore. Right? It's going to purely using motor. Okay? And initial gravity, spring, contact, friction, damping is going to take into account. Okay? And of course, if you want to go for task-based programming as well as plotting some parameters plot, right? And there is some external force, okay? You will need motion analysis. Right? Basically, motions and basic motion and motion analysis both involve physics, and motion analysis have the most complete pictures of it. Now, how about we just use these models in this case study, a Catapult, to go through the process of setting up a motion analysis. Okay. So let me first introduce these models. Okay, how does it work? It composed of several different components. Okay, we have an arm and a counterweight. Right, this is a very heavy stuff. Okay, then we have hand crank and gear assembly. Okay, what we do is we're going to rotate the hand crank, okay, so that the arm will actually lie down to here. Okay, and at the same time, of course, we are holding forces, and the counterweight is tend to throw the thing out, right? So what we do is when we are able to rotate this down, right? So we can see a pulley over here. We are not controlling the arm, but we are also controlling the gear assembly. What this gear assembly do is to trigger, you see a little door here, a little triangle, trigger this thing down so that the projectile can move into Catapult automatically. Right? Of course, there is a spring over there. Right? So there are several components to make this thing works. Right? Let's see how it goes. Right? So the first thing we do is set up a motor. Right? So we set a motor over here. You can see the directions. Okay? We're using a distant motor, a rotational motor. This is a motor setup. Right? It's 990 degrees. That's close to 3 circles. Okay. Then that's one thing we need to set, the power source. After that, we check for interference. Right. Of course, when the motor moves, okay, we can see that actually when the motor moves, it drives the gear and this thing moves to there. Okay. Obviously, we can see some interference. Right. Although we working in SolidWorks, it doesn't necessarily mean that they will have solid contacts. Right. It is a simulation element that has to be defined. Right. So inside motion analysis, there is a tool for you to detect interference along the time. Right? I'm sure you probably have used assembly interference detection, but that is a kind of a static detection, right? The tools inside motion analysis is kind of a dynamic interference. So you can see in what second and what second, what part is actually interfering some of the other parts. Right? By then, we can make our decision what solid body we need to define. In this example, is two of the triangles. Okay. So, how we define solid body contact is quite simple. Right? So we just, as usual, we do from top to bottom. Right? We select two of them. This, you can see the blue highlight selections. Right? And the next thing is material. Okay, so there is many default pairs of materials, right? The interference can be changed when the material pair is different. For example, the interaction between steel and steel is obviously different from steel and acrylic, right? So what this material affect is your friction properties as well as your elastic properties. Okay, so we have another things to define over here. This is the projectiles and the other parts. We still define contacts, right? For your convenience, you also can use contact group. So you can do a mass definition of contacts, right? So about the details of the contacts, frictions is quite an important input. Right? We have static friction as well as dynamic frictions. Right? So typically this could be found, there is plenty of resources on the handbooks or in the internet that allows you to find out the statics or kinematics frictions value for different pair of material. And of course, if your material is listed in our material database over here, there will be a default value to assign, right? Actually, down here. Other than that, I set up a spring. Right, to let the projectile out. Okay, so the spring we support, right? You can see this is a parallel spring and this is an axial spring. We support both of them, different kind of springs. Right? Is the most simple form of it is F equal to Kx. What we need to give is the K value, right? The spring stiffness. Other than this, we have the damping also. Now, what we define the spring is we'll put on this table, this 2 little tab over here. So it is invisible, but actually it's there. We no need to model out the spring to finish these simulations. Okay. By then, we can input the spring value and the free length. What a free length means is the spring length under no external force. Right? For example, here is 13, right? And the space over here is 9, right? Which means that actually when the projectile is loaded, right, the spring is on a compression state. Right? Once the door is open, right, the spring will serve as a loading mechanism, right? To pulse the projectile up to the up. Now, after everything is set up, right, just calculate the motions. Right? This example could be done in a few minutes, right? In a normal computers, right? You can look it again. Right? So this is how it works. The trigger will push the door down and the spring will instantly push the projectile up for the completions. Let's see again. There's a solid body contact downwards and push it up. All right. Let's have a look in the overall view. right? This is a massive destructive weapon, right? But it's always good to, there is always a lot of fun to use this kind of model to learn about simulation knowledge. Now, this is how it is. We cover Moto, right? Moto as a source. As you can see, we're not necessarily applying Motos in so many components. In fact, I have only one Moto here. Okay. Usually, we set it at the beginning of the motion, right? The driver part. Okay. Then we have context for some of the triggers, right? That is not covered by SolidWorks main. Okay. Or for other reasons, like we want to calculate the contact force, right? We want to know some detail force and stress generated over there, we use contact. Right? Otherwise, we use mid, right? Which is much more faster to calculate. Now we have used a contact to trigger the things, and we also input a spring over there, right? And it bounces up. Right? And you also can see the counter wave actually pulling down the arm, which means it includes gravity also. We also have set up gravity over here. Okay, so solid body contacts, motor, gravities, spring. We have used up 4 kind of motions elements over here, right? Which is as compared to finite element analysis and computational fluid dynamics, motion simulation is much more simple to set up, right? And the effect is quite amazing. It is quite a realistic animations we have over here. Now, it's just a few elements, but after that we can actually plot out some of the very interesting results. So these are some of the examples. Okay, we can actually look at the motor torque, right? By holding the motors, turning it and stop it, some of the projectiles coming in, we can actually see where the spike come from. Okay, this is a motor torque along with the time, right? So you can see to drive the motor, okay, actually is quite easy to drive it down, right? However, there is a spike coming up. Okay, if you look at the time, it is right over the time that the spring doing something at the time, which means it is about putting out the projectile on the arm, and the effect of the arm is reflected in the motor torque. Right? We have a match of the time and also the design parameter needed, okay, to successfully run this mechanism. Okay. How much does the spring force needed to bounce it out? Right? We run a few simulations to calculate the best spring. Right? What is the length of the catapult arm so that it can project out the stone much more farther? Right? What kind of material I should use to provide sufficient friction, right, when the projectile is hauled along the line. Okay, so there's all kind of analysis we can do inside here. Now, we have experienced how to set up a motion study. In fact, the element is quite simple, and we can see based on the result, we have a lot of things that we can leads to improvements, right? So I'm going to use another very fun examples to show you how to improve the design along the line, right? So I'm going to use a basketball to illustrate the examples. Okay, so here is even more simple. Okay, we're going to define context between our basketball and the boards. Okay, so also we assign initial velocity. Right, there is 2 components of them. One is 6 meters per second, which is a linear one. And as we know, we play basketball, we actually drag the ball a little bit. There's some rotation over there behind. And then we put gravity. Okay. So this is how it is. If we shoot on the penalty line, right, and we give that initial value, okay, it does not reach the ring. Right? We call it an aeroplane in Malaysia. Okay. So what we do is there must be a suitable parameters, okay, for us to shoot in that position, okay, that the ball will goes into the ring, right? Either is a net or rebound, right? Unfortunately, we don't know how much it is, right? That is always the design problem. We want the best parameters for lower cost consideration and also longer lifetime configurations, right? But it involves a lot of tests and errors, prototyping, for us to get through the right value, right? That's the same with the basketball, right? We only can increase our accuracy with a decent amount of time to practice the ball, right? So now, what we can do in simulation is to shorten that cycle, okay? We can use a tool called design study, right? Kind of optimization, right? Now what I do is I try to link the variable, right? My speed, the linear speed, right, of here, I'm going to test it out with a faster speed, 7 to 8, right? On a step of 0.125, which means 7, I'm going to test one time, 7.125, another settings, 7.250, right, until it's up to 8. So totally we're going to run 9 studies for this. Okay, and of course, what is the constraint of that? Okay, as a basketball problems, okay, the constraint is the balls go through the net, right? So this is quite a good tool. It's a displacement 2 is less than 0.111. Displacement 2 is measured by, you can see the blue dots and the blue dots, which is the center of the ball to the center of the ring. Okay. Okay, with some simple calculation of the radius, we can say that if the ball is within 0.111 meters, right, of two of the point, the ball will go through. Okay. So what this constraint actually is a sensor, right? We can do that trace all the information throughout the study, throughout this study time. It could take 5 seconds to run this for this whole scenarios, and in these 5 seconds, if the displacement have closed, I mean the ball is going to the ring, right? It will show up, right? This is we call a sensors for motion analysis. There could be many sensors. There could be wave sensors. When the things reach certain mass, right, it stops the motions. It could be proximity sensors. When we sense something that is close to certain range, it set an alarm. Okay, it could be displacement, it could be velocity, it could be acceleration. There's all kind of sensors you can put inside. Okay, even motor force or what. All right. So this is a simple one. What we run is we get a scenario, right? We got a list of variables changing in a logical way, in which we can start to find patterns on it to improve our design. Okay. So we have scenario 1. This one is 7 meters per second. If you shoot out a ball in these speeds, the closest we got is 0.3 meters. There's still a far to it. Right? We can check on the results. Right? It bounced the middle of the ring. Right here. So as we can see, the middle of the ring and here, okay, it is 0.3 meter. Okay. So how about we shoot it a little bit faster? Okay, let's see this. All right. It goes away. All right. So it bounced back. That's very close. We can know that if we increase the speed a little bit, right, this is a yin. Okay, we also can see on the chart over here, right, at what time we are reaching there. Okay, this is the minimum distance. We want the minimum distance to be as close as possible for the ball to yin. Right, let's see how it goes on the next one. 7.25, right, it's a yin. Well, this is a quite of a lucky one. Not a lucky one, but there is some Bowding's effect, right? Okay, so when this kind of context, we can say that the rotational effects actually can affect the movement over there. Some people spin the ball faster and the reaction could be different, right? Someone, if we accidentally doesn't aim very straight, it can possibly bounce to the left or right. Okay, so actually there is many parameters we can play with, okay, inside motion simulations. Now this is a close one, right? But it hit the front ring, right? We can say that we can find in the train that we still can move a little bit further for the perfect throw. Okay. Okay, so we have the perfect, close to the perfect throw. Okay, I think there's a mistake over here. It doesn't show up the middle one. But anyway, we jump to this 7.5, 0.2, right? It's not this one. This is the perfect throw. It goes through the net. 0.05, 0.2. In some case, we hit here, it goes up. All right. So it doesn't mean that this kind of shooting is a very accurate one. It doesn't mean that there is a range of parameters that we can get the balls right in. Inside there, there is some of the situation that we could not shoot the ball in. Right. And the next one, this is a rebounds. Right? It's a very nice rebounds, in which we shoot the ball right in after hitting the board. And this is also another rebounds. Okay, but we can see the path is that it's getting outward. All right. So we can see if you shoot higher, it can be going this way. All right, it's starting to come up. And of course, this is difficult unless we improve the spin. All right. The rotation effect and the friction effect can have a difference in these setups. Okay, so I think this is how we simulate basketball motions in the simulation. The setup is pretty simple. Right? You can adjust the value so that you can get the design parameters you want, or to generate the animation you want. Okay, so motion optimization is a very powerful tool, okay, to optimize your design. Okay, include all moving mechanisms. Okay, particularly in automations. Nowadays we use a lot of automatic handlings, machines. You do all the job for us. Right? Pick and place, transfer units, and also a lot of kind of mechanisms. Right? So the things to do for us is how we can apply the motion analysis for your design cycles. Okay? So I have listed out 4 key usage of motion analysis in the motion design. Right? The first one is to check for interference and clearance during motions. Right? We will use the dynamic interference to check all this. Is it possible that some of our parts are hitting each other, or some of the clearance is not enough or too much during the motions? Right? This could be checked, of course. Normally we drag our model in our assembly, right? But a tool for it could be useful when things become more complicated, such as an automation line. Okay. So the next thing is to solve kinematic parameters. Right? To calculate the force, torque, displacement, acceleration, path, so on and so forth, to graph the time and to analyze where is the high loading point, where is the lowest loading point, and whether we can make them balanced throughout the time. Right? It's always an interest for motion designers. Right? The third one is to optimize the mechanism. Okay? Taken this medical chair as an example. Okay, you can see there is a motor driving over here that will drive the chair up, right? And the gravity is downward. Okay, we can see that because of the angle effects, for some of the point that it would generate some force, which is roughly 2,100 Newton, okay, for this hydraulics to drive. Okay, so there is some design requirement, for example, to reach certain height or certain distance above, right? At the same time, it is possible to reduce or to change some of the design. For example, this pair of them, if I make this pair shorter, it could need more motor force or less motor force in some circumstance of the design. And for this and this, I can change it higher. I change it higher, the chair will be higher. This one, so I can change shorter. So which one is the best for the motor? Right? We can run the optimization like what we did on the basketball to find it out. Okay. For your information, the variables not only include the motion parameters, but also the geometry of your models, right? The length and width of your SolidWorks models. Okay, so this is the optimized mechanism. Okay. And the last one, and perhaps one of the most commonly used one, is to prepare a realistic presentations, right? So after you run the design study, you have your concepts, right? It is just one button to save the animation into your presentation as a window media player, AVI file, right? A lot of things. You can even render the files, right? So it looks like you have well prepared for your design concept, and this could be very helpful when we are talking to our customers, present it to our audience, because of the visualization and the motion things. So these are the 4 key capabilities I will highlight for SolidWorks motion analysis. Alright. So I guess this is the end of this webinar. Okay. So now it is a Q&A sections. Okay. If you have any questions or any information you want about it, you can click a little hands-on button over here. Right. You can see on your pattern, right? Your panel, webinar panel. Right. There is actually a little hand, in which you can press on it, and I can see your hands is raised up, right? And I will open your mic for for you to raise your questions. Right. In case you didn't find the little hand, or you don't have any audio device in your computers, right? You can find a chart over down there, okay? And you can type something to me. Right. So all kind of question is welcome. Okay. So in case you have, well, I see so far there is no questions. Okay. So in this case, you also can write to me in the futures if you need any information on this. Right. You can write to Sean@CAD-vision.com. Right. I'm supporting CAD and simulation products as well. Right. So feel free to write to me if you need any information on it. So thank you for joining this webinar. I hope to see you in next section. Okay. See you. Bye.